Hey everyone! So in the last video we proved the double angle identities for sine and cosine. And in this video I like to spend some time getting familiar with how to use these identities. And so what do these identities say? They say that if you know how to evaluate sine or cosine at some angle, these identities tell you how to evaluate sine or cosine at twice that angle. So before we really use these identities in all sorts of different ways, let's use one of these identities for an angle we're very familiar with, just to really feel how these identities work. And so let's go through one example of using this identity here. Cosine of 2 times x is equal to 1 minus 2 times sine squared of x. Maybe let's use this identity for the angle 5 pi over 3 and 5 pi over 6. So what I mean by that is if we evaluate 1 minus 2 times sine squared of 5 pi over 6, this is supposed to give us the same value as cosine of twice that angle, 2 times 5 pi over 6. And 2 times 5 pi over 6 is 5 pi over 3. And so I guess what I'm trying to say here is that let's say we didn't know how to evaluate cosine of 5 pi over 3. The idea is that we can use this expression on the right involving 5 pi over 6 to evaluate that expression. And maybe if you're more comfortable with degrees than you are with radians, the idea here is that we're using the angle 150 degrees, sine of 150 degrees, to evaluate cosine of twice that angle, 300 degrees. And so let's evaluate this right-hand side. So we get 1 minus 2 times sine squared of, actually let me rewrite sine squared of 5 pi over 6 as, well, that's equivalent to sine of 5 pi over 6, evaluating that first, and then squaring this result. And so what is sine of 5 pi over 6? Well, here if we look at our unit circle, 5 pi over 6 is 30 degrees shy of a pi radian rotation around our circle, right? So here it's 150 degrees. And so here this is 5 pi over 6. And this is a 30, 60, 90 triangle that fits underneath this angle to the horizontal axis, right? So this gives us 1 minus 2 times, well, this distance here, this is 1/2. Okay, so this is 1/2 squared. And so when we continue evaluating this, we have 1 minus 2 times 1/4, which is the same as 1 minus, well, 2 times 1/4, that's 1/2. And so we actually also get 1/2 here as a result. Right, so this was to evaluate cosine of 5 pi over 3. Cosine of 5 pi over 3. And so what we've really done here is that we've used this angle 5 pi over 6, we've used our understanding of this angle 5 pi over 6 to evaluate cosine of 5 pi over 3. So, cosine of this angle all the way out here. And so this agrees with our understanding of cosine of 5 pi over 3, right? So 5 pi over 3, this is 60 degrees shy of the full 2 pi rotation around our circle. So this is a 30, 60, 90 triangle. And cosine is the x-coordinate of this point on the unit circle, and that's exactly 1/2, like we expected and like we've produced here with this double angle identity. So one thing I like to warn you about is that here, if we were to look at this expression cosine of 2 times x, above we've written down all these different identities for what cosine of 2 times x is equal to. And I just want to reiterate or make the warning here that this is not the same as 2 times cosine of x. Right, so we cannot factor out that 2 inside the input of this function and pull it out of the function itself. Here, so let me put a big warning sign here just to really emphasize that this is not true. We cannot factor out that 2 outside of the input. And maybe let's just go through one quick example to show, one explicit example to show that this is not true. And maybe let's use the same values we saw above, 5 pi over 3 and 5 pi over 6, right? So let's say we wanted to evaluate cosine of 2 times 5 pi over 6. Well, we saw that earlier. That's the same as cosine of, well, double 5 pi over 6 is 5 pi over 3. And we just evaluated that to be 1/2. Oops, sorry, that's not cosine of 1/2. This comes out to be 1/2. And well, if we take 2 times cosine of what we're calling x in this case, 5 pi over 6, well, 2 times cosine of 5 pi over 6, that's what is cosine of 5 pi over 6? That's the x-coordinate on our unit circle, the horizontal coordinate on our unit circle, corresponding to that angle of 5 pi over 6, and we see that that's the negative square root of 3 over 2. And so this is 2 times negative square root of 3 over 2, and that comes out to be, well, that's a negative square root of 3. And so really this just goes to show that these are not equal. We cannot pull out that factor of 2. If we want to do anything involving cosine of 2 times an angle, we'll have to use our double angle identity if we're not familiar with what the value is already. So for many of the angles that we know how to evaluate sine and cosine at, we actually already know how to evaluate sine and cosine of twice those angles. For example, if I wanted to evaluate sine of 7 pi over 6, well, we can do this by, drawing out our unit circle. And here's 7 pi over 6. Well, that's 30 degrees past 180 degrees. Right, pi over 6 past pi, and so this comes out to be about here. And we end up with the y-coordinate of negative 1/2. And so let's say I wanted to evaluate sine of twice this angle. Right, so sine of 7 pi over 3. Well, twice this angle, that comes out to be about here. And, well, 7 pi over 3, that's pi over 3 past 2 pi, or in other words, 60 degrees past 360, right? So the full rotation and then an additional 60 degrees on top. And so here we have a 30, 60, 90 triangle. This is going to give us a y-coordinate of the square root of 3 over 2 on the unit circle. So we know how to evaluate sine of twice our angle, twice 7 pi over 6. So the double angle identities for sine and cosine aren't really going to help us evaluate sine and cosine at twice an angle we're very familiar with, because we already know how to evaluate sine and cosine at twice those angles we're familiar with. What they're really going to help us do is evaluate sine and cosine from information that's not the angle itself, or they're going to help us manipulate expressions. So really that's where the double angle identities are going to shine. So let's take a look at this example where we want to evaluate sine of 2x, cosine of 2x, and tangent of 2x, given that cosine of x is equal to negative 2/3, and that this angle x lies in quadrant 3. And so let's start by trying to evaluate sine of 2x. So to evaluate sine of 2x, we can use our double angle identity, that sine of 2x is really equivalent to 2 times sine of x times cosine of x. And here, we already know what cosine of x is equal to, right? Cosine of x we're given negative 2 over 3. And so to evaluate sine of 2x, all we need to know now is what sine of x is equal to. And so how do we get sine of x from cosine of x? Well, here we have our Pythagorean identity to do so. right? So here we can recognize that sine squared of x, actually maybe I'll do this in a slightly different color, sine squared of x plus cosine squared of x, this is always equal to 1. This is really just rewriting our equation for our unit circle. And here we know that, sine squared of x added on with cosine squared of x. Well, cosine is negative 2/3, so here we have negative 2/3 squared. This is going to give us 1. And so sine squared of x plus, well, what is this? This is 4 over 9. This is equal to 1, giving us that sine squared of x is equal to 1 minus 4 over 9. And 1 is the same, right? 1 is the same as 9 over 9. So when we subtract away 4 over 9, we're left with 5 over 9. Right? 9 minus 4 gives us 5 over 9. And so here, to get sine by itself, right, we take plus or minus the square root of both sides. This gives us sine of x is equal to plus or minus the square root of 5 over 9, which is the same as plus or minus the square root of 5 over the square root of 9, where the denominator would come out to be 3. Right? The square root of 9 is 3. And so which is it? Is it plus square root of 5 over 3, or is it minus square root of 5 over 3? Well, maybe let's draw a picture. So here we're looking at a unit circle, and we're given cosine of our angle is negative 2 over 3. So cosine of some angle giving us negative 2 over 3, that gives us the horizontal position of negative 2 over 3 on our unit circle. So we might end up either here or here on our unit circle. But we're given that our angle x lies in quadrant 3. And so if our angle x lies in quadrant 3, we're really considering this point here below. And so what should sine of x be? What should sine of our angle be? Well, it should come out to be negative. Right? So here we really have negative square root of 5 over 3. That's what sine of x is equal to in our scenario. So if we go back up here, so now we know that sine of x is negative square root of 5 over 3. And so this gives us, well, here if I have a negative quantity times a negative quantity, we're going to end up with a positive quantity. So this is 2 times the square root of 5. That's 4 square root 5 over 3 times 3. That's 9. Sine of 2x is equal to 9. So next, let's evaluate cosine of 2x. So here we have 3 different identities for what cosine of 2x is equal to. And so cosine of 2x, this can be seen as cosine squared of x minus sine squared of x. It can be seen as 2 times cosine squared of x minus 1, or 1 minus 2 times sine squared of x. These are all valid ways of computing cosine of 2x. And so here we can use whichever one is most convenient for us. In this case, we've actually figured out sine of x already, we've figured out cosine of x already, so all of these different identities we can use right away now. If we wanted to evaluate this expression, or this cosine of 2x, at the beginning of the problem, we actually could have, because we were given cosine of x is equal to negative 2/3 in the very beginning of this problem. So without having to do much work, we could have actually evaluated cosine of 2x right away by using this identity here. So maybe let's go through the motions of using this identity. So here cosine of 2x, well, this is equal to 2 times cosine squared of x minus 1, and we said that cosine of x was negative 2 over 3. So we're going to take this, we're going to square it, and take away 1 after doubling it. So this is, well, 2 times squaring negative 2/3 comes out to be positive 4/9. And then this gives us, well, this gives us 8 over 9 minus 1. And this gives us negative 1 over 9. So this is what cosine of 2x is equal to. And the last thing we wanted to compute was tangent of 2x. So tangent of 2x, we didn't talk about a double angle identity for the tangent function. There are double angle identities out for the tangent function, but here we can just use what we know about tangent, that it's the same as sine of our input angle divided by cosine of our input angle. And so here we've already figured out that sine of 2x was equal to, what was it? It was 4 square root of 5 over 9. And so this is 4 square root 5 over 9. And then cosine of 2x we just evaluated as negative 1 over 9. And so here we can divide these two fractions, right? We can rewrite this as 4 square root 5 over 9 multiplied with the reciprocal of our dividing fraction, or this would be 9 over 1, negative 9 over 1. And so these factors of 9 in the numerator and denominator would cancel each other out. And we would just get that this is equal to negative 4 square root 5. So that's what tangent of 2x is equal to. Negative 4 square root 5. So let's briefly summarize our results from this problem in a picture. And let's use our picture above. So in this problem, we started with some angle that we didn't know was in quadrant 3. And we were given the x-coordinate, or the horizontal coordinate of this angle x. And we needed to find the vertical and horizontal coordinates of the angle 2x, or twice this angle. And so here, if we look at this angle, it's quite a bit past 180 degrees. And so this will be, quite a bit past 360 degrees when we look at double the angle. In fact, that double the angle comes out to be, roughly here, right? So here's our angle. If we go around the unit circle once and then a little extra, this is our angle 2 times x. And what we did was we found the horizontal and vertical coordinates of this point on the unit circle here. So here this is cosine of 2 times x, sine of 2 times x. And so if we look at our results, they kind of make sense. If we look at sine of 2 times x, this is 4 square root 5 over 9. And this comes out to be approximately 0.994. So very close to 1, very close to the tallest or highest y values on our unit circle, as this picture suggests. And if we look down here, cosine of 2 times x, that's negative 1/9. So some very small negative number to the left of the y-axis, or the vertical axis, and that's what we have in our picture here. So here, this is just to give us some more intuition about what we're really finding when we go through a problem like this. So probably the most important thing to take away from our new double angle identities is that we can use these identities to manipulate expressions. And here, maybe just to give us an example of this, let's verify this identity: cotangent of x minus tangent of x is equal to 2 times cotangent of 2x. Let's see where we can use the double angle identities to accomplish this. And so here, when we want to verify an identity, again, we want to show that one side is equivalent to another. So we want to take one of the sides of this equation and just manipulate that one side and see if we can manipulate it into the other. And so usually we want to start with the more complicated looking equation, or part of the equation, the more complicated side, and see if we could simplify that into the other side. And here, usually it's harder to take a term and break it up into multiple terms. So let's start with this side here with multiple terms. Maybe we can combine it into a single term. So here let's start with cotangent of x minus tangent of x. Well, we can rewrite this as, this is cosine of x over sine of x, right, for the cotangent. And then tangent, well, that's sine of our input angle divided by cosine of our input angle. And we can make a common denominator to subtract these two fractions and write them as a single fraction. And to make a common denominator, well, the first fraction has a denominator of sine, the second fraction has a denominator of cosine, so the common denominator will need to have a factor of sine and cosine together. So let me multiply this first fraction by cosine over cosine, giving us cosine squared of x over sine of x times cosine of x. And then let me multiply the second fraction by, this needs a factor of sine in the denominator. So here let me multiply by sine of x over sine of x, giving us sine squared of x over, I wanted to write cosine squared of x, but that would be wrong, right? We want sine of x over cosine of, or sine of x times cosine of x in the denominator. And now there's a common denominator, we can actually subtract these fractions, giving us cosine squared minus sine squared, right? Subtracting the numerators of this fraction, and then here we have the same denominator, sine of x times cosine of x. And here, looking at this top fraction, or the top part of this fraction, the numerator, it looks like a Pythagorean identity, but it's not, right? So the Pythagorean identity says sine squared of x plus cosine squared of x is equal to 1. And here it's very important that there's a sum between this sine squared and this cosine squared. And this difference tells us that we can't really use this identity here. But what does include this identity, cosine squared of x minus sine squared of x? Well, that's the double angle identity for cosine, right? Cosine of 2x, one of the double angle identities here is cosine squared of x minus sine squared of x. And so here I can replace cosine squared of x minus sine squared of x. I can replace that with cosine of 2x. So here this is cosine of 2x over sine of x times cosine of x. And so why does this help? Well, if we look back at what we're trying to accomplish, we want to show that our original expression is equivalent to 2 times cotangent of 2x. Right, and so here maybe I should say that cotangent of 2x, well, this is cosine of 2x divided by sine of 2x. And then here we also have this extra factor of 2. And so we've already got this cosine of 2x in the numerator, we just need to show that the denominator has a sine of 2x. And this looks almost like one of the double angle identities for sine, right? So sine of 2x is equal to 2 times sine of x times cosine of x. So we're only missing a factor of 2. And so one thing we can do is we can multiply the numerator and the denominator by 2 to give us this extra factor. And now we can replace that 2 times sine of x times cosine of x with sine of 2x. So this is 2 cosine of 2x over sine of 2x. And now we're done, right? Cosine of 2x over sine of 2x, that's cotangent of 2x. And then we have this factor of 2 in front, and here this is what we were asked to show in the first place. So let's take a look at another example here where we want to find all of the solutions on the interval from 0 to 2 pi of this equation here. And so what makes this equation a little bit challenging to solve is that there's this cosine of 2 theta. And typically cosine of 2 theta and cosine of theta give quite different results. And this prevents us from being able to use many of our algebraic tools to solve this equation. For example, we can't really factor so well when we've got cosine of 2 theta and cosine of theta floating around in our equation. And so one thing we'll want to do is we'll want to try and replace this cosine of 2 theta to make this equation a much more manageable one, maybe one that we can factor. And usually we'll want to try and make an equation into one involving just one sort of trigonometric function. And so here when we look at the different options for how we can replace our cosine of 2 theta expression, we can replace cosine of 2 theta with cosine squared of theta minus sine squared of theta. We can replace it with 2 times cosine squared of theta minus 1, and we can replace it with 1 minus 2 times sine squared of theta. But because our equation involves cosine of theta, and I don't want to incorporate a sine of theta into our equation, let's use this identity here where we make the replacement that cosine of 2 theta is equal to 2 times cosine squared of theta minus 1. So let's replace cosine of 2 theta with that, giving us 9 times 2 cosine squared of theta minus 1 is equal to 9 cosine squared of theta minus 4. And so we've made a replacement here. And so now if I distribute this 9, we get 18 cosine squared of theta minus 9 is equal to 9 cosine squared of theta minus 4. And we can try and get that cosine squared of theta onto one side, giving us, subtracting away 9 cosine squared from both sides gives us 9 cosine squared of theta on the left, minus 9 is equal to negative 4. And if we add 9 to both sides, we get 9 cosine squared of theta is equal to 5. And so here I just see the squared part of this trigonometric function just almost by itself. One thing we can do here is we can try and apply the square root to both sides. And here, maybe just to make this as clean as can be, let me first divide 9 from both sides. So you get cosine squared of theta by itself is equal to 5 over 9. And then we can take plus or minus the square root of both sides, giving us the square root of 5 over the square root of 9, which is 3. And so now we just have to solve these equations, that cosine of theta is equal to positive square root of 5 over 3, and cosine of theta is equal to negative square root of 5 over 3. Any solutions to these two equations will be solutions to our original equation. And now these values here, as x-coordinates on our unit circle, these aren't very familiar values here, so we can't really use our understanding from our special right triangles to solve these equations. We'll need to resort to using inverse trig. Maybe just to give us some sense of what we're finding here, if I draw out our unit circle, what we're doing here is we're finding the angles which give us an x-coordinate of positive square root of 5 over 3, and points on our unit circle, angles that give us x-coordinates of negative square root of 5 over 3 on our unit circle. So really we're looking at, any angles that bring us to these points here. And so here if we take inverse cosine of square root of 5 over 3, this is going to give us, I should write approximately, it's going to give us an approximate value for one of the angles, and it only gives us an approximate value for an angle between 0 and pi. Right, so only on the top part of this unit circle between 0 and pi. And so this gives us 0.7297 radians. That's this angle here. And then here if we take cosine inverse of negative square root of 5 over 3, well, we're going to get an approximate angle for this point here that lands at this point here between 0 and pi. And so this comes out to be 2.4119. And so how do we get the angles on the bottom half of this unit circle between 0 and 2 pi? Well, here, one fact about cosine is that cosine of theta is really the same as cosine of negative theta. And so I know that this angle down here, at least one angle that brings me to this position, is equal to negative 0.7297. And that's not an angle between 0 and 2 pi, right? Angles between 0 and 2 pi are positive. But if I added 2 pi onto this angle, then we would end up with the angle between 0 and 2 pi. That brings us to this bottom coordinate on the right. And we can do a similar thing here, right? So here, this angle, at least one angle that brings us to this position, is the angle negative 2.4119 radians. And again, this is not an angle between 0 and 2 pi, but if I added 2 pi onto this angle, we would end up with an angle between 0 and 2 pi. That brings us to this position here. And so here we've listed out two of our angles, and we've found two of our angles earlier as 0.7297 and 2.4119.